Hi and welcome to video 8 on this series on sampling and confidence intervals, and this is Unit 5, Topic 4 of Math Methods. Today we're going to talk about margins of error, which is a continuation on our video of confidence intervals from last lesson. So you recall that an A% confidence interval is this interval here, from p hat minus the z-score for A times by this thing, which is our standard deviation, but in terms of p hat and n, to p hat plus the z-score of A times by the standard deviation. So remember, this comes from z equals x minus mu over sigma, and x therefore equals z times sigma plus mu. And that's the rearrangement there. So we're trying to find those x values, the boundaries for p, and we're doing it this way. We've got z times sigma with that additional mu there, but because we're looking up and down, we've got that minus and then we've got that plus there. So that's our confidence intervals. There's a little bit of a review for you, and if that's the case, then we have this E is equal to that thing there. So E is equal to this, which is this part of our confidence interval. We've got p hat minus E and p hat plus E, and E is called the margin of error. So what happens is, if we've got a p hat here and we want to calculate a confidence interval, a 95% confidence interval, we will do a calculation such that we get our confidence interval will be evenly spread on either side of p hat, and therefore we will be 95% sure that the actual population proportion p lies in this range. It'll be some value in there. We're 95% sure of that. What we actually get is, because we're starting with p hat and then we're actually subtracting E, and we're actually adding E. So the width of our confidence interval is 2E, and E is this thing, and that's called the margin of error. So you may be asked to calculate the margin of error. The margin of error is z times the square root of p hat times 1 minus p hat over n. So just keep that in mind, and remember our confidence interval is E below the sample proportion and E above the sample proportion. That's the boundary of our confidence intervals. So let's have a look at some examples of this. For a sample with p hat equals 0.7, calculate the margin of error for a 95% confidence interval when n equals 10, 100, 1000. And then for what value of n will we attain a 1% confidence interval? Now, the concepts here might become part of a bigger confidence interval question, but by recognizing that if we want to find the width and what's happening with our confidence interval as we increase n, we don't need to worry about this part of the calculation. We don't need to worry about this even. N only affects the margin of error, so we only have to deal with the margin of error to get a bit of an idea of what's going on. Anyway, let's do this. I'll just move example 3 down. We'll get to example 3 a little bit later, and we'll run through this. So first, we've got p hat is equal to 0.7 and n is equal to 10, and our z, because it's a 95% confidence interval, is equal to 1.96, and so therefore error, and I'll call it error 10 for an n equals 10, is equal to z times the square root of p hat 1 minus p hat over n, and in this case 1.96 times the square root 0.7 times 0.3 over 10, and that's equal to 0.284. So I'll do it to 3 or 4 decimal places, and in this case that 95% confidence interval for a low n value actually turns out to be like that. 0.284 is a fair way below 7. It's a fair way above 7 for the upper bound. It's 98. So in terms of p hat being a proportion and therefore can't be greater than 1 because it's probability based, that's pretty close to 1. It is worth keeping in mind here that NP is equal to 7, n times 10 times 0.7, but NQ is equal to 3. So it actually fails one of our tests. So it's not a very good sample if you've only taken 10 in this case. But that's how we calculate it. I'll quickly do 2 and 3. So E100 is equal to 1.96 times by the square root of 0.7 times 0.3 over 100. And that's equal to 0.0898. And so you can see that that is considerably better than this. It may be 3 times better. And we've increased the sample a fair bit though to get that 3 times better. But our 95% confidence interval has shrunk, and that's really important in many industries. E1000, if you can take a sample of 1,000, is 1.96 times the square root 0.7 times 0.3 over 1,000, and that's equal to 0.0284. So this is really interesting here, because 0.0284 is 10 times smaller than this. And 1,000 is equal to 100 times 10, and the square root of 100 is the difference between those. I mean, have a think about it. That makes sense, because if we write our E out, E is equal to Z times by, and I'm going to write it slightly differently. Well, I'll do this way first. P hat 1 minus P hat over N, which could be equal to Z times by the integral, the square root of P hat 1 minus P hat over the square root of N. And so, because we've got the square root of N, and it's the one factor that's changing because we're only changing N, well, we can see how that multiplying N by 100 is going to change it by a factor of 10, because we're dealing with a square root there. So that's really interesting as well. So that's part A. So for part B, the question states or asks, for what value of N will we attain a 1% confidence interval? And I've just realised that this really is probably quite poorly written. In summary, so I'm going to take this 1% confidence interval and I'm going to change it to something more like, we attain a confidence interval with a 1% range. So the point here being that I want my confidence interval, because we have a p hat of 0.7, to be from 0.6, that's not meant to be there, 695, 0.7 to 0.705. That confidence interval there would give a range of 0.01, which is 1% statistically, probability based. And that's what this is, it's a probability based question. So my question is, how do I gain that 1% confidence interval, which is 0.5% above and 0.5% below my p hat? So let's have a look at this mathematically then. I want my confidence interval 95 to be from 0.695 to 0.705. And that means that I want p hat minus E, p hat plus E to meet those criteria. And so I'm going to take, let's say I'll take this one, p hat plus E has to equal 0.705, which means that E, because p hat is 0.7, has to equal 0.005. And 0.005, that should have an extra 0, is equal to 0.5%. That's our 0.5% above, and that's our 0.5% below. There's where our 1% comes from. So that reworded version is a lot better. Now, I want that E to be 0.005, and so of course I'm going to go back and put in my E value and determine the N value that will allow that to happen. So I'm going to zoom in here as we're doing this working. So my E value comes from Z times P hat 1 minus P hat over N, which equals 0.005. Now, I'm very much for doing the rearranging before I substitute in. I do know that Z is equal to 1.96. I do know that P hat is equal to 0.7, but I'm going to substitute in after I've rearranged. So the rearrangement's not too hard. First, I'll do one step at a time. P hat 1 minus P hat over N is equal to 0.005z. And then I take a square of both sides, I get p hat 1 minus p hat over n is equal to 0.005z squared. And then I'm going to flip it over. So I get n over p hat 1 minus p hat is equal to 1 over 0.005z squared. And then I'm going to multiply that p hat times 1 minus p hat. And there are a couple of ways you could have done this, same result. But I get n is equal to p hat 1 minus p hat all over 0.005z all squared. Z is equal to 1.96, p hat's equal to 0.7, and so n has to be equal to at least 2186.589. So we'll say it has to be equal to at least 2187. That's what our n value must be equal to in order to reach that 1% confidence interval. Because as you increase our n value, we decrease the range of the confidence interval. So we decrease our e value, which is our margin of error. And that's pretty reasonable, because if I go back up to the 1,000, remember my confidence interval had this, which was 2.8%. But increasing by 2,000 is a fair jump.